In this video, I will be deriving the A and B coefficients for the van der Waals equation. The van der Waals equation is P equals RT over V minus B minus A over V squared, right? And so the first thing we need to do is take the first and second derivatives with respect to volume, right? So dP dV equals minus RT over V minus B squared, right? Because we multiply by the power, which is -1, and then reduce the power. And for the left side, we multiply by -2. So we have 2a and v cubed on the bottom. Then taking the second derivative, we have, again, multiplying by power and reducing by 1, we have 2RT over v minus b cubed minus 6a over v to the fourth. Now at the critical temperature, we can say the first and second derivatives will both be equal to 0. So if we go ahead and evaluate these at the critical point, we will be using critical temperature and critical volume for each of these. And now we can say those are equal to 0. Okay. Now if we do a little bit of massaging, if we add this first term to both sides, we have 2a over vc cubed equals rtc over vc minus b cubed, or sorry, vc minus b squared. And for this second equation, if we add the right side to both sides of the equation, we have rtc over vc minus b cubed equals 6a over vc to the fourth. Okay. Now we can see these are pretty similar, and we can actually see if we were to flip these around, we can actually get a lot of terms to cancel out. So if we go ahead and flip this bottom equation here, we have vc minus b cubed over 2rtc equals vc to the fourth over 6a. And now if we multiply, right, if we multiply these two terms, and if we multiply these two terms, we can get bc over 3 equals bc minus b over 2, right? And so now it's just a little bit of algebra. If we multiply by 2 on both sides, we get 2/3 vc equals vc minus b. And then solving for b, we just add b on both sides, subtract the 2/3 vc. We get b equals vc over 3. Right. And we can use this value now to calculate a, right? So if we take this equation here, we can substitute b. We will have 2a over vc cubed equals rtc over vc minus vc over 3 squared, right? And so this right side becomes rt over 2/3 vc, right? And so that will be 2/3 vc squared, which means we have 4/9, and that is on the bottom. So we can go ahead and flip that around. So 9/4 vc cubed vc squared. And now from here, it's just some simplification, right? So you can see a is on this side. If we multiply by vc cubed over 2 on both sides, we get a by itself. So A equals 9/8 RTC times VC, right? And that's our A value. Now, if we want to find these at a critical pressure and a critical temperature instead of a critical volume, which is much harder to calculate or measure, I should say, we can go ahead and the ideal gas law says P equals RT over V, right? Because we are using 1 mole and we just divide by V on both sides. So we can say at the critical point, the critical pressure is equal to R times the critical temperature. Or sorry, we want to evaluate that volume. So we have volume equals RT over P. Right? So the critical volume equals R times the critical temperature over the critical pressure. Right? And now substituting in for volume, we have B equals RT, or R times the critical temperature, over 3 times the critical pressure, and A equals 9/8 times R squared times critical temperature squared over critical pressure, right? So now I'm going to go ahead and erase most of this just for cleaning up the board. All right, so we have our original equation where A equals 9/8 R squared TC squared over PC. I'm actually going to write these back in with the volume because that's easier to evaluate the compressibility factor, right? So B equals VC over 3, and A equals 9/8 RTC over VC, right? And so now I'm going to find the compressibility factor, right? So we have this original equation here, P equals RT over V minus B minus A over V squared, right? If we write in B and A and evaluate at the critical point, right? Because we are finding the compressibility factor at the critical point, so that's where we're evaluating it. We have critical pressure equals R times the critical temperature over V critical volume minus V, which is critical volume over 3, minus A 9/8 R times critical temperature over critical volume will be cubed, right? Because we have the critical volume squared and critical volume, right? So if we do some simplification, we get PC equals RTC over 2/3 VC, right? And if we go ahead and flip that, we will have 3/2. So 3 RTC over 2 VC minus this equation, 9 RTC over 8 VC cubed. And we can see something ain't right here. Oh, why did that is not over VC, that's why. RTC times VC. Yeah, we are multiplying by critical volume, that's my bad. So here we have RTC, and VC over VC squared means it is over VC, And now we can see in both sides we have RTC over VC, RTC over VC. So if we take that out, we have RTC over VC times 3/2 minus 9/8, right? Creating a common denominator here. 3/2 times 4 over 4. We have 12 over 8 minus 9 over 8, and that will be 3/8, right? So multiply by 3/8 here, and this 3/8 is our compressibility factor, right? So at the critical point, the compressibility factor is 3/8. Now I will be generating pressure diagrams using the van der Waals equation of state. All right, so the first thing we want to do is import NumPy, and then from plotly.subplots, we will import make subplots. Right? Oh, that should be an underscore, not a plus. All right. Now we want to define our function, right? So if we define van der Waals pressure, right, because we were finding the pressure, and we use variables volume and temperature, right? Those are our inputs. We can see here the equation of state. This is what we will return because we are finding the pressure. So we will return R times T over V minus B minus A over V plus sigma times B times V plus epsilon times B. All right, and I will surround this entire bottom part in parentheses. Okay, is that correct? Yes. All right. So now we see we need our alpha or our A value, B, sigma, and epsilon. Right. So if we scroll down to this parameter assignments table, we can see sigma and epsilon are both equal to 0. All right, so let's set those equal to 0. I will leave them in the equation because even though this bottom part right here, it will just end up being v squared, right? And epsilon and sigma really kind of go unused. It's a lot easier to translate to some of these other equation of states if we just leave them in for now. So now we have our A value, right? A, we can see here, psi 27 over 64, and our alpha function is just 1. All right, so 27 over 64 times R squared, critical temperature squared, over critical pressure. I don't know what that was. All right, and then our B value. All right, we have omega, so 1/8 times R times critical temperature over critical pressure. Right? Now we have all of our variables in this return function, but now we need our R, our critical temperature, and our critical pressure. Right? So R, of course, is our gas constant, 8.314 joules per mole Kelvin, right? And our critical temperature and critical pressure, we will look up here. So water critical properties, the temperature, 647.096 Kelvin, and our pressure, 22.064. Oh, that didn't copy. 22.064. Okay, I don't know what's happening there. Anyways, we will write that in with E6 pascals. All right, so now we have all of our variables within the function. We can actually check this here, right? So if we just input, we'll say 1 meter cubed and 350 Kelvin, and we do get a pressure that is positive. That's good. I'm just going to make sure that when I increase the volume, the pressure is halved, right? That looks good. And when I increase the temperature, the pressure goes up. All right, so that looks good. Now I'm going to create a line space, right? So we have a range of volumes. And if we go ahead and do 0 to 100 with 1,000 data points, np.linspace, sorry. All right, and plug that into our van der Waals equation. So we'll have V, and we'll say 350 Kelvin again. If we scroll all the way to the top, we have negative infinity, right? Now, why is that? Well, in this case, E times V and sigma times V are both 0, right? So this bottom part ends up just being V squared, and V squared is 0 when volume is 0. So we get a negative answer, or sorry, we get infinity. Another problem we can see is that this V minus B, when the volume is less than B, this term will be negative. And that means that we will end up with a negative pressure, which is not good. So we actually need to make sure that we have a value greater than B. So if I go ahead and copy this B out here, do 1.01 times B, right? So 1.01 times B, that means that our volume is always going to be greater than B. And we enter this. All right, now we have no more issues, right? We have positive pressures. You can see this one is a lot higher than the others. That's because of how little space there is, right? Because it's only 1% more than B. It's not a lot of extra space because B is the space taken up by the particles, right? So there's not a lot of space for them to move around and everything. The pressure becomes very high. So now we are going to graph this. Right, so we are going to create a figure. Figure make subplots. And we will do figure dot add a scatter plot, right? Where our x value is our volume and our y value is our van der Waals equation using our volume, and we'll say 350 Kelvin. And I want to make the mode markers. So we just have a bunch of points. And all right, so here's our graph. You can see here, there's our 1 point that's a lot higher than the rest, and everything else just flatlines. So if we were to change the range here, right? So figure dot update y-axis, and we edit the range. We'll say 0 to 1e4. All right, so now we can see a lot more, but it's still flat lines, right? I mean, we can't really see the change here. And we can see this is very logarithmic. So the way we can fix that is by creating a logarithmic scale, a logarithmic x-axis, that is. So we'll use np.log space, right? And we'll take the log base 10 of this 1.01 times b. And we don't want to use 100 anymore, right? Because 10 to the 100th power is a very large number, right? We don't want to go that far. we will go with 0, right? So up to 1 essentially, right? Because 10 to the 0th power is 1. And we will also, let me move this to the bottom. We will also update the x-axis. So our type is equal to log, right? So we have a logarithmic scale. And something, oh, well, we want to change our range, of course. So we'll go up to here, and we will include negative pressures. Let's go a little bit higher. All right. So here is our van der Waals equation for a graph at 350 Kelvin, right? If we were to go to 400 Kelvin, right, we can see it's essentially the same. But now what we want to do is actually show that difference, right? We want to show a range of different temperatures. So I can make here for T in NP dot a range, right? So we want a range, and that is 275 Kelvin to 900 Kelvin. We will go by increments of 25. We will do that, and if we go ahead and hit enter here. All right. Oh, we do not want 400 every time. We want our temperature. All right, and as soon as this loads, oh, I'm not going to use markers here because you can see that's very messy. So lines. All right, now it looks a lot nicer. And here we have our van der Waals equation of state evaluated at a range of different temperatures across the volumes. And we have, if we look here, we can see a little dip in each of these, right? So these are below the critical point. And we can actually see the critical point if we zoom in. It's this light blue one right here, right? So it's, oh, you know what? I'm going to title these real quick. So name equals our temperature in Kelvin, right? Okay. So now we can actually see the temperatures here. If we zoom in here, right? So we can see this is very flat, right? That's our inflection point at the critical point. And that is where our first and second derivatives are both equal to 0. We can see here about 650 Kelvin, and if we look up, yep, 647, that's very close. So this is actually a visual representation of our critical point, right about here-ish. And we can also, using this graph, we can see here, I'm going to eliminate all of this area, right? So we'll go to 0.01, which is -2, right? 10 to the -2nd. All right, and now if we zoom in here, and I'm going to eliminate a bunch of these. We'll single out 550. How about that? All right, so looking at 550 Kelvin, at a given pressure, right, there are 3 volumes. All right, okay, so as I was saying, so when we have a Maxwell construction, we can actually find the vapor pressure at a given temperature by determining where, if we have a given pressure and we integrate, this area in this bottom curve and this area in this upper curve are equal, right? So at that point, or sorry, at that pressure, that will be our vapor pressure. at the given temperature. And we have this first curve here, right? That will give the volume of the liquid at that temperature. And this last part here, this third intersection, will give the volume of the vapor at the given temperature. Right? And so that's something we will do in a future video. But for now, this is it. Oh, so if we look at this, okay, so if we look at this, we can see at higher volume or at higher temperatures, right? The vapor follows the ideal gas law. But then as we go further and further down in temperature, eventually we have a graph with an inflection point, or sorry, a curve with an inflection point. And that inflection point is our critical point. So that's right about here, right here. You can kind of see where the graph flattens out. And then after that point, we have dips in volume, right? And we will be using Maxwell construction to actually determine what the vapor pressure at the temperature is and what the volumes of liquid and vapor are. All right. And that is all for now. Thank you.